Hello and welcome to another video. Alright, so in this video I will be deriving a formula for rotation in 3D space. And so this rotation will be specified by an axis located at some point, and there will be some kind of point that you want to rotate about that axis. And that's going to be called P, which is the point we want to rotate. A will be the vector that represents the axis, and P sub A will be a point on the axis. And this will occur in the XYZ Cartesian coordinate system. And the 2D rotation matrix was pretty simple, so this shouldn't be too bad, right? Nope, that is wrong. That is very, very wrong. Actually, 3D rotation formula is scary. This thing scared me and shook me to my core. I'm telling you, this thing is a beast. And in this video, I'll explain exactly why I think this. Alright, so the first step in explaining why this thing is scary is setting the scene. Alright, so let's set up a Cartesian coordinate system where we have x, y, and z axes. We will have our points right there, and the axis, and a point on the axis. The axis will be denoted as A in terms of basis B1, which we'll explain later. We'll have a position vector denoting the position of P, which is our point that we want to rotate. We'll have a position vector denoting the point P sub A in terms of B1 basis. That's just a point on the axis that is used to specify the position of this axis, and we have right there, we explain it. Then we also have the blue ball, as we explained. And so our XYZ coordinate system is something that we will call B1. It's our B1 basis. And a basis is just something that that you need to describe every single point in space. So it's a pretty simple concept. It's just a fancy word for that concept. So what we're going to do here is that we're going to say that if we want to represent some vector v in terms of basis c, then we're going to put those brackets around the vector, and as a subscript we'll put down the basis that we want to express it in terms of. So for example, we have P expressed in terms of B1, and that's that blue ball right there that we show in this slide. So what we have here is a diagram with our rotation plane and path added. So you'll see that our path is within this rotation plane in green that is perpendicular to the axis. So it's that green plane that kind of looks like a lawn, looks like a lawn, with grass. And within this grassy lawn is the circular trajectory that your point follows around the axis, and that's in red. So it's basically the path spray paint. Sorry, it's that path in red that is spray painted on the lawn that you see over there. But what we want to do to make the calculations easier is to actually shift this thing to the origin. I'll show you what I mean. Alright, so this is exactly what I mean by shifting everything to the origin. So we want this. We want the plane and the axis to have a point that is located at the origin. So we want this, but how? How do we get there? Well, in the next slides, I will show you exactly how. Alright, so step 2 in explaining why this thing is so scary is defining the plane that we want to rotate about and shifting everything to the origin. So first, we will shift the whole setup such that P sub A is now located at the origin, aka subtract P sub A from each position vector to obtain your new vectors. And there's a picture of what we're doing, and here we just shift everything by P sub A. And note that we do not shift the axis because it's not a position vector. We don't really need a position to define the axis. the position of the axis is defined by the points on the axis, P sub A. And note that we create new points, and we create them with these primes, that apostrophe symbol, to denote the new points. Alright, so we have shifted this entire setup such that P sub A is located at the origin. And now, we will define a new vector, which will be the vector pointing from the origin to that red ball right there. And this red ball is in the center of the circular path that was spray painted on the green lawn. And this circle, the red ball is on the plane of rotation. And so this vector will be your axis vector scaled by some amount because it's located on the axis vector. So the scaling factor will be T sub PL, or TPL. So A times TPL will be our expression that describes this new vector, pointing to that red ball. And also note that we have this black vector, and the black vector is located on our plane, and it connects the red and blue points. So the head of the vector is located at the point that we want to rotate, or the blue ball, and the tail is located at the red ball, which is our the A times TPL. And this black vector will actually help us later down the road in defining our new coordinate system, but we're not there yet. So right now we're going to use this thing to help us define our rotation plane, because we haven't done that yet. So we'll do that now. Alright, so now we have this this equation over here that says that the dot product between these two vectors on either side of it is equal to 0. This means that they are perpendicular. It says that the black vector must be perpendicular to the axis. And this expression in the parentheses will be the black vector, whereas the one that's not in parentheses is your axis. Then again, we have the ATPL, that is your position vector that describes that red ball. And TPL, as I've described in the previous slide, is your scaling factor. And so we can deduce from this equation that TPL is equal to that stuff right there in green. Alright, so now that we've solved for TPL, we know ATPL, which is the position vector describing the red ball. And so now we're going to shift everything such that ATPL is now located at the origin. Okay, we will subtract ATPL from each vector to obtain new vectors. And these new vectors will be denoted as, in terms of primes. We'll have a P sub A double prime representing the new point on the axis that was shifted by ATPL, and P double prime as your new point that you want to rotate around the axis that is shifted by ATPL as well. And as you can see, your ATPL is located at the origin now. So now we've shifted this effectively, we've shifted this entire setup to the origin such that the red ball is located at the origin. Alright, so here is our new setup that is shifted to the origin. And so one huge advantage of doing this is that the vector that describes P double prime is now located on the plane. So this thing, this thing is exactly the same as our black vector now. And our black vector was located on the plane. And so we can actually use this thing to make a new coordinate system that is located on our plane. And so this is going to be very important to making this new coordinate system and deriving the formula. Alright, so step 3 in explaining why this thing is so scary is defining the new coordinate system that will be located on our plane. And I will show you what I mean. Let's define a new coordinate system and call it B2. B2 will simply be a rotated version of B1, so all length scales remain the same. So in order to define this new coordinate system, we need the unit vectors in the directions of the three axes. So we'll have unit vector ZPL be along our new z-axis. It's not really the z-axis, but it's the equivalent of the z-axis. And this will be in our B2 coordinate system. And we'll define ZPL as, or ZPL hat as A double prime over the magnitude of A double prime in terms of B1. And in doing this, we will ensure that Z hat PL is in the direction of A double prime and of magnitude 1 as measured in B1. So now XPL will be the equivalent of the x-axis in our B2 coordinate system, and it will be located, it will be in the direction of P double prime and of magnitude 1 as measured in the B1 coordinate system. And x hat PL will actually be located on our plane, because remember, P double prime is also, the vector pointing to P double prime is entirely located on our plane, because remember, it is congruent with that black vector. So if we have XPL hat and ZPL hat, then how do we get to YPL hat? Well, according to the logic of the XYZ coordinate system and using the right-hand rule, we could say that YPL hat is equal to ZPL hat crossed with XPL hat. So, and this is in terms of B1, and yeah, so YPL and XPL will actually be located on our rotation plane. And it's kind of like the XYZ coordinate system, but it's just rotated pretty much. Alright, so essentially what we've done is that we've defined a new coordinate system, and we called it B2. In this diagram, B2 is described by the unit vectors x hat PL, y hat PL, and z hat PL in the yellow arrows. It is the yellow arrows that are the unit vectors in B2. And so the x hat PL and y hat PL unit vectors lie on our plane of rotation, and the z hat PL vector is perpendicular to the plane of rotation, and it lies along our axis. So what this means is that we can actually use the 3D rotation matrix for rotation around the z-axis to rotate our point. So this makes things much easier, and we will apply it in the next slides. Alright, so there's a slight problem here, and this problem is that our point that we want to rotate around the axis is expressed in terms of B1. It is expressed in terms of the x hat, y hat, and z hat unit vectors in the the B1 coordinate system. But we want this to be expressed in the B2 coordinate system, so that we could apply the rotation matrix around the z-axis. So how do we get there? So we need a way to switch from the B1 to B2 coordinate system. But then we're also going to have to switch back, because once we have the rotated point in the B2 coordinate system, we need to switch it back to the B1 system so that we could figure out the formula in terms of the XYZ Cartesian coordinate system. And so right now we're going to do this. We're going to figure out a way to switch between the two coordinate systems. Alright, so we have expressions for z hat PL, x hat PL, and y hat PL in terms of the B1 coordinate system. So we have the expressions for the unit vectors within the B2 coordinate system in terms of the unit vectors in the the scaled unit vectors in the B1 coordinate system. So So right now we're just going to solve for the y hat PL in terms of B1, because we know it's the cross product of z hat PL and x hat PL, and so we get this thing right over here. All right, so now we have the x hat PL, y hat PL, and z hat PL unit vectors within the B2 coordinate system expressed in terms of the B1 coordinate system. Specifically, it's expressed in terms of x hats, y hats, and z hats, which are the unit vectors in the B1 coordinate system. So we have, more specifically, we have x hat PL expressed in terms of the B1 is this linear combination of x hats, y hats, and z hats, which are again the unit vectors within the B1 coordinate system, the XYZ Cartesian coordinate system. And so we're expressing basically all of these in terms of what we already know. We already know the components of the axis. We already know the components of the point that we want to rotate. Those were given in our formula. So yeah, we now have expressions for the B2 coordinate system in terms of what we already know. All right, so we can summarize these equations, make them more compact by expressing them as a matrix. So if we multiply the x hats, y hats, and z hats unit vectors in the B1 coordinate system by this matrix over here, then we get the x hat PL, y hat PL, and z hat PL unit vectors in the B2 coordinate system. So we've effectively figured out a way to switch from the B1 unit vectors. So we basically have a way to switch from B1 to B2. So we have a way to express the x hat PL, y hat PL, and z hat PL unit vectors in terms of the B1 unit vectors of x hat, y hat, and z hat. All right, so now we could actually get the so in the last slide we switched from B1 to B2, but now we can do a switch from B2 to B1 by inverting the matrix. So if we take the inverse of this matrix and multiply by the XPL, YPL, and ZPL as the inputs, then we could get the X, Y, and Z as the output. So yes, we have a way to switch from B2 to B1 as well. All right, so let us summarize what we found here. So we basically found that that we have a way to express x hat PL, y hat PL, and z hat PL, in other words, the B2 coordinate system in terms of B1 on the left, and then on the right we have a way to switch from the B2 coordinate system to the B1 coordinate system. So we have a way to express x hat, y hat, and z hats in terms of x hat PL, y hat PL, and z hat PL. So yeah, so we have a way to switch between the two coordinate systems, which is exactly what we need. All right, so now the penultimate step in explaining why the rotation formula is so scary is rotating our translated point P double prime in the B2 coordinate system by using that rotation matrix that I was talking about earlier, the rotation matrix around the z-axis. All right, so now let's first express P double prime in terms of the B2 coordinate system. So we have P double prime in terms of B1 is P sub x double prime times x hat plus P sub y double prime times y hat plus P sub z double prime times z hat. Therefore, P double prime in terms of B2 is P sub x double prime multiplied by x hat in terms of b2 plus the rest of the stuff. And so one thing to note here is that x hat in terms of b2, y hat in terms of b2, and z hat in terms of b2, they will all be expressed in terms of a linear combination of x hat PL, y hat PL, and z hat PL, right? So, and we have a way of converting x hats in terms of b2, y hat in terms of b2, and z hat in terms of b2 into a linear combination of, the b2 unit vectors, x hat PL, y hat PL, and z hat PL. However, these expressions were way too long to show on, in this presentation. It kind of scared me. This is so long that's scary, and yeah, I'm frightened by how long how complicated these expressions were. I was like, whoa, All right, so we will now rotate p double prime about our z-axis, in quotes, because it's not really the z-axis. It is the z-axis in the, well, I guess it is the z-axis in the b2 coordinate system. So we will call the rotated point p double prime rot. And we get this rotated point in terms of b2 by multiplying the p double prime in terms of b2 by the rotation matrix for counterclockwise rotation about the z-axis. And that's all there is to it. And this is our illustration of what we're saying here. Pretty cool. Alright, so now here are some more illustrations of p double prime and the rotated version of p double prime in our plane, as seen from the b1 coordinate system on the left. And then on the right, we show it within our plane that is located in the b2 coordinate system. And in this plane, the way that's shown here, the z hat PL will actually stick out towards the screen. And as you can see, it rotates counterclockwise in the x hat PL, y hat PL plane. So that's what's going on there. So our sixth and final step in explaining why this rotation formula in 3 dimensions is so scary is undoing the translations to find the location of p rot, which is our rotated point, our point that is rotated in the, around the axis in terms of the b1 coordinate system, the XYZ Cartesian coordinate system. Alright, so first we need to switch back to the b1 coordinate system. So we have our rotated points, p rot double prime, but it's in terms of the b2 coordinate system. But we want to express it in terms of the b1 coordinate system. So again, we have p rot double prime in terms of b2. We have the expression for it, but I'm just expressing everything in terms of symbols. But because it's too long to show on the screen, but this is the general form of p rot double prime. It's going to be a linear combination of x hat PL, y hat PL, and z hat PL. And again, we know those factors in front of the each of those vectors, unit vectors. But I'm just not showing it because it's too long to actually show on the screen. So anyway, p double prime rot in terms of b1 is equal to each of those 3 factors multiplied by each of the unit vectors in the b2 coordinate system in terms of the b1 coordinate system, that is in terms of a linear combination of x hat, y hat, and z hat. And once again, we have a way to solve for x hats. Or sorry, we have a way to solve for x hat PL, y hat PL, and z hat PL in terms of B1. But once again, this is way too much to show on the screen. The expressions are way too large, so I'll just keep everything in terms of these symbols, just to make things simple. Alright, so now we will undo those translations that we did in the first step, where we translated everything from from the 1 point space to the origin. So we're going to undo that, and as shown right there in that illustration below. And yeah, so we're going to undo those translations by, instead of subtracting, we're going to add this time. And there we go. We have p rot prime in terms of B1. Then we get to p rot in terms of B1, and that's exactly what we want. And we have it now. Alright, so awesome. We have our point that is rotated around the axis in terms of B1, and this is in terms of things that we know. It's in terms of the point that is located on the axis, which we know, in terms of the axis vector that we know, and in terms of the points, the original points that we want to rotate, and we know that too. So we have the rotated points in terms of things that are known. So awesome. So what is this formula exactly? Well, it's kind of scary, to be honest. And it's best that I show you MATLAB because, you'll see why. Yeah, that's pretty scary. That is scary. Alright, so here's the same formula, but it looks a little less scary because we see that it follows some kind of form right there, and those numbers are just defined. There's just a bunch of numbers, a bunch of variables that are defined within that equation. So it's pretty long, but at least it has some kind of general form to it. Alright, but does this thing work? Did I write the correct formula? Did I drive the correct thing to rotate a point around an axis? Well, it seems like I did, because I wrote a MATLAB program that graphs the axis right there in blue, the point on the axis in purple, or magenta actually, and the original point is in red, and the rotated point is in blue, or dark blue. And we see that it's the rotated point and the original points lie on the same rotation plane, because that circle right there in orange is actually a circle within the rotation plane that is perpendicular to the axis. So as you can see, the rotated point is clearly a rotation of p around the axis. Then we also have the green point, the light green point right there is the reference point at 0, 0, 0. Alright, so here's the MATLAB code that I used to write this program. And this program actually gave me the formula for rotation around the axis in 3 dimensions, given the axis as a vector, a point on the axis, and a point that you want to rotate around the axis, as the inputs. And your output was the rotated points around the axis. So that's the code I used. I used an example to create that plot in the last slide, and it seems like everything works. So that's pretty cool. I was pretty excited when everything worked. Pretty cool. All right, so that's it. The lamb jumped over the cow jumped over the moon jumped over the planet. That's it. So yeah. Alright, so that was the end of this video, and I hope you enjoyed it. And as you can see, the 3D rotation formula, it may have seemed scary, but if you take a closer look, then it's really not that scary. It's not too scary. It follows a form, and we've kind of demystified the derivation behind this formula. I actually learned a lot myself. I didn't know how to drive this thing until I kind of thought about it. I was like, oh, what if you use a different coordinate system on the rotation plane? And that's how I did it. And there's another way to drive it. You could drive it using the 3 principal rotations, rotation around the z-axis, y-axis, and x-axis. But it's this whole big and complicated, it's like several operations using these 3 fundamental matrices. It just gets a little confusing, but I think this is a more intuitive way of driving it, and yeah, that's basically it. So yeah, so have a great day, or if it's nighttime, then have a good night, and I will see you in the next one, the next video.